It is visible, sir. Clear.
The audio is also okay?
Yes, sir.
Audio is also audible?
Yes, sir. Yes, sir. It is audible.
Okay, I'm ready.
Yes, sir. We'll start.
Good evening, sir.
Good evening.
Ramesh here.
Namaskar, Ramesh.
Namaste, sir. Thank you very much for your accepting our invitation to give a guest lecture, sir, today. In spite of,
Thank you very much. Also, the timing is convenient.
yeah, that's right, sir. Even for us also. Anyway, I welcome all the participants who have joined through YouTube for this guest lecture. And Professor Ashok Rao is a well-known mathematician, and of course we call him as a mathematician and former professor from IISc. A brief introduction of Professor Ashok Rao will be given by my colleague Dr. Govind Raj.
Good evening, sir.
Good evening.
I welcome all the participants who have joined the live stream over the YouTube for this guest lecture on pedagogy and applications of linear algebra. I think Professor Rao needs no introduction, but still I want to. So I'll just give a brief introduction about the speaker today. He holds a BE, ME and a PhD all in electrical engineering from Mysore University in the year 1982, in the Indian Institute of Science, Bangalore in the year 1985, and Indian Institute of Technology, Bombay in the year 1991 respectively. He has over 30 years of teaching and research experience, which includes 6 years in IIT Bombay, 7 years in IISc Bangalore, 4 years in NITK Surathkal, the rest in various places in India. He has successfully guided PhDs both in E&C and computer science areas and has over 100 publications. He is also a solar photovoltaic specialist, having been trained by Siemens Solar California during the year 1996 and 1997. Earlier, he was head network project at CEDT, IISc Bangalore from 1999 to 2005. It was a project funded by SDC, Swiss Agency for Development and Cooperation. To his credits, he has got many awards, out of which I'll just name a few. He is a gold medalist from IISc Bangalore during 83-85. He has been awarded Texas Instruments International DSP Design and Education Award for promoting excellence in undergraduate DSP education during 96-98. He has received citation from Philips Company for regularly crafting excellent UG students in E&C, electronics and communication, in the area of signal processing and digital communication during the year 96-98. He is among the very few across the world to be invited to make a presentation in Pan IIT 2006 Global Meet. He is also an entrepreneur, having successfully started and managed several IT and renewable energy companies during 1998 to 2011. From 1999, he has been a consultant on design of DSP and multimedia systems to many companies, to name a few: Philips, NXP, that is Star TV, Textronics, Honeywell, Toshiba, Sony, Infineon, Texas Instruments, Analog Devices, LG, etc. From 2007, he has been a guest and visiting professor at IIM Bangalore, teaching PGPP and PGSEM programs and executive MBA programs there. He teaches entrepreneurship and public policy courses there. He was senior advisor for research, Government of Kerala, Department of Technical Education from September 2013 to March 2017. He has participated and mentored, incubated numerous startups in Bangalore over the years since 1999 till date, some of which have matured into good companies as well. There is an invited talk in TEDx talk given by Professor Rao, which is available in YouTube. You just search Professor Rao TEDx talk, you will find it. He is one of the very few to have taught courses and done research in multidisciplinary areas, and institutions like IIT, IAC, NIT, and IIM in India. Now I request Professor Ashok Rao to give a talk on pedagogy and applications of linear algebra. Please, sir.
Thank you very much. Very elaborate introduction. You could have made it brief. Anyways, the title of the talk is Pedagogy and Applications of Linear Algebra. Currently, I'm in Mysore, and I hope to live here for many more years, particularly after the COVID. Okay, my mail ID is ashokrao.mis@gmail.com. Thank you very much. Very elaborate. So, what is linear algebra? I mean, many of you would have studied in various contexts, but I think one of the earliest encounters we have is Kramer's rule, what one calls elementary row operations in solving systems of equation in a more mature way of the type Ax equal to B. So today, linear algebra means systems of equation. Even though all the machinery and rudiments of linear algebra came like this, and also these ideas of vector spaces, subspaces, basis, dimension, more elegantly as a matrix representation, which is just around 200 years, even though idea of determinants precedes idea of matrices. But among the last subjects to mature and evolve has been matrix theory. So whenever you have matrix representation, the classical aversion to matrices is to suggest matrix inversion as a difficult problem. Modern methods of systems of equation Ax equal to B is strongly associated with an idea of orthogonalization, which is what we are going to use very strongly, and a name which is quite recent compared to ideas of this Gram-Schmidt orthonormalization, a famous algorithm which also motivates people to do algorithmic approach to linear algebra, which is computational linear algebra and algorithms for solving efficiently systems of equation Ax equal to B, many times poorly conditioned also. Of course, one talks of Gaussian elimination, which is also related to linear algebra, which is related to solving systems of equation. It has all the things that we look at Kramer's rule and particularly elementary row operations, so on and so. We have had a lot of stray bullets about this, but very few of us perhaps have gone through a very systematic program in linear algebra. But more interesting, how did all this come about? You must clearly know that nice things do not happen suddenly. COVID is a very good example that bad things happen very suddenly, okay? Why nice things do not happen suddenly is because they are baked in an oven of space and time. So over various places and over x-axis of time stretching quite a lot, these things are done. Many minds work on this to beat it to perfection, which means it's a very evolutionary thing. Nascent ideas, stray ideas, perhaps not connected with each other, have developed. It may also have cultural and social factors in it, because mathematics is a cultural entity. It definitely has a lot of social impact, and social impact also makes mathematics, in particular linear algebra, better. It may have developed due to economic reasons. That's how strong use of numbers in society has been. There may be unrelated events that have shaped it. Quite perhaps some stray merchant has taken some idea from somewhere. He had nothing to do with it, but it caught on somewhere else and eventually developed to what we see today. We will see some of these or maybe all of these ideas now. But what I can assure you is it is indeed a fascinating journey to see how these things have shaped. And I'm very sure there's such a fascinating journey is there in almost every topic, if only people spend time and dwell on that. Okay. Now the question to ask is, we are giving this talk on this, but why does anybody want to study linear algebra? Okay. Definitely linear algebra is one of the branches or topics in maths, and it has been associated with numbers. So it can be put as a part of the numerical literacy of society, where people have been using numbers for counting, which predominantly is by act of commerce and taxation and stuff like that, which is where most people started using numbers. Okay. It definitely has become more sophisticated over the years, and particularly linear algebra is now the cornerstone of modern technology, simply because uh, computing has become very common and widespread, to the point that many of you participants have a very smart phone, which is almost as powerful as the mainframe computer that I used to use about 30 years back. Okay. But one basic idea of linear algebra, that is of solving a system of linear equations, has been part of various evolutions in civilizations. We'll see that, because it's not really a new subject as we make it out, even though the mature part of linear algebra in terms of, say, eigenvalue, eigenvector, singular value decomposition is very new, but the ideas behind this is as old as the civilization. And again, mathematics is so widespread, yet divorced from culture. So it's a strange thing that the idea for maths in general is either fear, hatred, or anxiety, and the other extreme is love for it. So there doesn't seem to be a middle ground where people slowly enjoy without fear or not get too passionate, so on and so forth. So the middle ground is missing in this. Particularly, it's also a gender sensitive topic, in the sense that quote unquote, traditionally women are not good in maths, or not were not allowed to be good in maths, and even today large number of ladies go to life sciences thinking that they can avoid mathematics, but they get stuck with statistics down the line. Okay, so I think numbers cannot be avoided in general. Okay, so where do we look for these things? We definitely have to look for ancient civilizations. So ancient civilizations relate to terminology or subjects like archaeology and anthropology. Then the question is, how old is old? We could do 500 current era or even earlier. And if you look at anything 500 current era, AD is not used anymore, 500 current era and earlier. And this comes out with this list. The people then earlier to 500 current era were the Mayans, the Egyptians, Chinese, the Hindu or the Indian as you can call it, the Greeks, Romans, Mesopotamians, and of course the Arabs and the Africans. Okay. So it rules out the Europeans and Americans, who definitely were nowhere in the picture. If you look at anything beyond the 500 current era and earlier, that doesn't look anything about the Europeans and US. Okay. Now, of all the ancient civilization, Romans are ruled out. Okay, they were experts in gladiator thing, and they have been exporting very bad leaders all over the world, including India. Okay, but the Arabs, who were as old as anybody else, were never keen to learn anything other than learning that involved trading and communication, because trade meant communication, communication meant trade, and very interesting, they actually communicated very important part of mathematics to the southern part of Europe, which started the Renaissance. The best name that comes to my mind is Fibonacci. Mayans, who were isolated in South and Central America, they did something about their own calendar, but that calendar did not end the world in 2012 as everybody in their calendar were expecting. Africans definitely had better things. They had better things to worry about than linear algebra. So they were more worried about wildlife and doing more of anthropology than archaeology, and the classic statement of out of Africa obviously justifies that. So that leaves us only the five others. Nothing to do with Mayans, nothing to do with the Romans, nothing to do with Arabs and Africans. So it leaves out the Egyptians, Chinese, the Hindu, Greek, and the Mesopotamian cultures. So we'll see what they were doing. One of the most ancient civilizations, obviously, is among them has been Egyptian, and they were using linear algebra or the ideas of linear algebra, not linear algebra in the modern context. They were using it for commerce and taxation, and this is a famous document in a papyrus sheet which contains about 84 short mathematical problems together with their solutions, and dates to about 1650 BC. It's about 4,000 years old approximately. And the 40th problem is this. So when deciphered, hieroglyphics deciphered, it looks like this. It simply says divide 100 hectares of barley among five men in arithmetic progression, so that the sum of the two smallest is 1/7 the sum of the three largest. Okay. So you have a measure that has to be divided unequally among five, and the unequal is not random, but it has an order of arithmetic progression. Okay. Or such division of resources among people in unequal ratios is quite common historically. You will see that even in the famous Mahabharata, where Kunti and her children go to the forest and they live on uh, begging, collecting alms and food every day, and all the things that are collected are actually brought together, and the portion is divided into two parts. Half of what collectively they collect is given to Bhima. The other half is divided among five others, four brothers and the mother. Okay, so even today, now that the Supreme Court has ruled differences, a division of resources unequally among elder brothers and all is quite common. Okay, culturally, I'm not saying. So if you really want to solve that, you say, okay, let A be the least amount and D be the common difference. So then the four men receive A plus D, A plus 2D, A plus 3D, and A plus 4D. I know the total is 100, so the sum of all is 100. And there's also a condition which says 1/7 the three largest is equal to the two smallest. So if you put this into a system of equation, you get 5A plus 10D is 100, 11A minus 5D equal to 0. Today you can solve this, but they were not really solving in the way we do it now, but they did it in a very interesting way. Today, if you put it, you can have 5, 10, 11 minus 5, A, comma, D equal to 100, comma, a system of equation AX equal to B, and try solving. Okay. What I did was interesting. The solution that's there in the papyrus document simply says guess a value. Okay, just case let A be 1. Now you substitute that in the fourth equation, that yields D equal to 11 by 2. So I substitute A equal to 1 and D equal to 11 by 2 in the third equation. That LHS gives me 60, whereas RHS is 100. So LHS is not equal to RHS. The solution is not correct. So we just guess the initial value of A by multiplying it by where it has failed. So 100 by 60, and that leads to the correct value. You substitute back in the fourth equation, that gives you D is equal to 55 by 6. So the quantities of barley received the 5 people are 10 by 6, 65 by 6, 120 by 6, 175 by 6, and 230 by 6. And it works well. So this technique of guessing a value by an unknown and later adjusting it has been used by many cultures throughout the ages. And today the famous Kalman filter just does this. The most famous of something that tracks trajectory or a profile, whatever you call that, is really, including the stock market, is the famous Kalman filter. And what it does is just this. It makes an initial guess of a solution, uh, predicts the answer, verifies with updates, takes the difference, which is the error, uses the error to correct the initial estimate, and progressively people know that in certain conditions it actually converges very well to an amazingly accurate value. So this idea of just guessing, checking how wrong you are, correcting it, is that's the kind of thing that they were doing. And of course, the way they were storing is the famous papyrus roll and Alexandria library. What remains of the Alexandria library is this today, the old building. And there is some connection with Joseph Fourier. We'll see that here later. And today, the old sketch of the old library and what has been restored and rebuilt again, thanks to United Nations funding, the Alexandria Library looks like this, even though Alexandria is no more the center of learning in the world like it used to be in those days. Okay. There now. So, Alexandria Library, more than Alexandria Library, the Alexandria town is interesting in the sense that when Napoleon captured Alexandria or the Egypt and Fourier was made the administrator, it's interesting that Fourier was one of the persons indirectly responsible for deciphering the hieroglyphics. Okay, that's interesting contribution by Fourier, which not many mathematicians know because they are more relating Fourier with Fourier series, but Fourier did better work as a non-mathematician than as a mathematician, and he did excellent work as a mathematician. So you can see his other work was much better. Okay. Now, what about their cousins or contemporary civilizations like Mesopotamians? Okay. They were using linear algebra ideas in again division of resources like land. And this is the details of the Babylonian Empire, famous Hammurabi Code and the Hanging Gardens of Babylonia. So many would know that. They were putting this material on clay because the Euphrates and Tigris Valley had rich alluvial soil and stuff like that. And this is how they also were the earliest to start writing. So these are the cuneiform tablets of various kinds, which depicts some documentation. And the very famous library in Mesopotamia built by Surbanipal. This is how they were. This is a document or a book and stored in such shelves. And one particular clay tablet depicts a problem which in English would look like this. So the problem on the clay tablet is this. It says a trapezoid with an area of 320 square units is cut off from the right triangle by a line parallel to one of its sides. The other side has length 50, other side has length 50, and the height of the trapezoid is 20 units. What are the upper and the lower widths of the trapezoid? Okay, what is y, what is x? So such division of odd dimension land is quite common in cities where you get at the edge of a road, two roads intersecting, not correct, not perfect square or rectangle, odd dimension sites or auction. Very common even today. I think there is one advertisement in a newspaper today for this. Today, okay. So how did they solve? I mean, so let x be the lower width and y its upper width. The area of the trapezoid is height times the average width, which is so 20 into x plus y by 2 is 320. And using similar triangles, x by 50 should be y by 30. So the solution to these generate an interesting system of equation. Half of x plus y is 16, half of x minus y is 4. You add and subtract, you solve. X is 20, y is 12. Now you notice this equation 3 and 4. If I now put this in modern linear algebra form in a matrix form, it's going to be half, half, half minus half, x, y equal to 16, 4. So this matrix representation of this system of equation looks like half, half, half minus half, or 1, 1, 1 minus 1 outside half. This is one of the world's most used matrix today, and I'll come to that later. Uh, so they didn't put it in the matrix form, but this is what it led to. Okay, we weren't very far behind. We were a little peculiar. I'll come to that. They were also using ideas of linear algebra in commerce and resource allocation. They did not do much of the systems of equation type, but more in terms of equivalence type of system, more famous by the Aryabhatta's identity of nx plus dy equal to 1. Okay. So this is a document from a village called Bakshali, which is today in Pakistan. But the entire manuscript, I am told, is either in Oxford or Cambridge University Museum. It is a copy from 4th century AD, but many of the material comes from earlier times. Okay, so this is the sample of the birch bark on which the manuscript is written. And that the problem says the following. One merchant has one breed of horse, 7 Asava horses. The second has another breed of horse called the Haya horses. And the third merchant has 10 camels. And there's a typical camel for cattle trading context, very common even today. Only thing, you now deal with money. Those days you would do barter. So you would probably give 2 buffaloes and pick a horse, or give 2 horses and pick a camel, whatever. That was the kind of, I mean, you couldn't do half camel, 1/4 of a horse, nothing like that. Okay. So they are all equally well off. That is, all their values are equal. If each gives 2 animals, one to each of the others, and then find the price of it. So there's the equivalent system of equation. I had 7 horses, so I keep 5 horses, give one to the one who has the higher breed and the other which has a camel. If I do that, the value is some k, which is same as the one with 9 Asava horses. He gives one to the higher breed and one to the camel, that is big. Then somebody had 10 camels, he gives one to these 2 with the horses and keeps 8 the values. So given this 3 system of equation, can you solve for the values x, y, and z? Okay. The manuscript describes how it is solved, and today you can actually do this by taking LCM, which is the lowest possible solution, and you can do that. So if you solve this, you are going to get x equal to 42, y equal to 28, and z equal to 24, and the total value is 262, or multiples of 262 is also permitted. Okay. So numbers and solving systems of equation have been there all along, and so did our painful neighbors today, but those days they were not painful. They were actually very friendly neighbors. They also had something interesting. They had a very similar document which says history of Chinese maths by this Chui Chang Sean Shu, the 9 chapters of mathematical art. It's a collection of 246 problems and their solution. You see, all those days they were writing problems and the solution very similar to what you do in Sham series today. Okay, Sham series is a very popular book simply because it allows you to learn with the teacher, without the teacher, in spite of the teacher. Okay, yeah. So it could be even earlier, because frequently books were copied. The number of copies were very few because there was no printing. The 8th of its 9 chapters, which is entitled The Way of Calculating My Arrays, it contains 18 word problems that leads to systems of equation in 3 to 6 unknowns. And the first of this 8th chapter problem is just this. There's a farmer who's grown some vegetables, 3 bundles of corn. We all know that farmers, when they grow in a plot, on an acreage. There's no uniform growth. Some are overripe, some are correctly ripe, and some are underripe, or whatever. Some are pest infested, some are very good, some are too young. But nevertheless, they harvest it once in a week or once in 10 days because market appears once in a week historically. Okay. So they brought it, and many farmers would do similar because every neighbor farmer grows very similar crop as happens today. So there are three farmers with this variation. Then the second one has two of the first, three of the second, one of the third, and the last farmer has first of the one of the first kind, two of the second, and three of the third. They all make that 26 measure. So it's like this system of equation. If you put it as x, y, and z to be unknown, the first farmer has 3 kg of the first kind, 2 of the second kind, and 1 of the third kind. He values it at 39. This fellow has 2, 3, and 1. He values it at 34. The third fellow values it like this. It is at 26. Okay. So how they were doing is they were actually putting it in a column form. These are the variables 1, 2, 3. Okay. 2, 3, 26. 1, 2, 3, 26. 1, 2, 3. So 2, 3, 1, 34. 2, 3, 1, 34. So on column. And they were actually using abacus. So now you see why in the Oriental kingdoms like China, Southeast Asia, including Hong Kong, Taiwan, they actually, many businessmen, even in the shop, still trust the abacus more than the calculator. Okay. So they would put this and do what one calls elementary column operation, not elementary row operation like we are more familiar today, and eliminate one variable at a time. And they would get a triangular system of equation, solve for this, back substitute, get this, back substitute, get the other. So when you solve, you get these answers. And all the things we do in modern linear algebra is built here. Okay. So these ideas, what they call counting boards or abacus, moved from China to Japan, and by 17th century, Leibniz actually solves 3 equations in 3 unknowns by a method of determinants. A few years later, Gauss solves it by what is today known as Gaussian elimination. So what Gauss does is systematically streamlines a very commonly known idea more than 1500 years before him. Okay. Oh, what about Greeks? You cannot leave them because the Greek influence on maths, including geometry and algebra, is profound, and we cannot. So, if they were doing that, they must have been doing something about linear algebra too. Okay. The first hit we get is regarding Archimedes with a very famous problem called the Archimedes celebrated cattle problem, which he apparently posed it as a challenge to his colleague, a very interesting colleague called Eratosthenes. People who do number theory would know C of Eratosthenes for factorizing the primes. Okay. No solution has come down from ancient times. We don't know whether they were able to solve, but the problem was posed very well. Okay. And this is a problem statement. Let's not go into the story. It's very big. It's a herd of cattle grazing, and there are 4 kinds of bull, there are 4 kinds of cow, and all these patterns, etc., all that. One can read on the internet the details of this problem. And this is Eratosthenes. Okay. So if you put it, conventional desecration of the 8 variables is this problem: white bulls, black bulls, yellow bulls, dappled bulls, then white cow, black cow, so on and so forth. If you look at all their conditions, the system of equation looks like this. Okay. So you have actually 1, 2, 3, 4, 5, 6, 7 equations in 8 unknowns. So it will have infinite solutions. The final solution is this. So the final answer when solved was this. It is this huge number times k, where k is the smallest positive integer. Uh, Please note this was first time solved in mid 1960s using a mainframe computer. So I don't think Archimedes or Eratosthenes or any contemporary of them would actually try to solve this, but they made them challenging to interest others to think. This is the statement of the problem, and you will see all the problems in the past are also statements about. So, historically, mathematics meant stating a real life problem in words, converting it into symbols, associating numbers with it, solving it. In the process, commerce and economics and other things would happen, but slowly a technique also got developed. Okay. So we move a few thousand years and push to a modern situation where most of the modern problems are first attempted in the language of linear algebra, because uh, if I put it in the form of ax equal to b, I can do many things. I can solve, and we all know that ax equal to b has three kinds of solutions: an exact solution, an approximate solution, or a least square solution, whatever. Okay, so which simply means that ax equal to b always has quote unquote a solution, may not be exact, but at least very close to it. And if there are infinitely many things close to it, you could pick one under some constraint. Okay, so the best formulation of a problem in modern language is to put it as ax equal to b, and the worst solution is solving it as a inverse b, because matrix inversion is an exceedingly bad problem, even though matrix formulation is pretty universal. So what really happens is, in why linear algebra has become a universal subject is, formulation is different. Very many people take different boundary conditions, physical parameters, constraints, and etc., and formulate a given engineering, physical, economic, or whatever problem as a system of equation. However, once the problem in any domain is formulated as a system of equation, solution is very straightforward. You have to invert a matrix, or you have to invert a matrix without explicitly inverting, so on and so forth. Okay. So what it means is there may be 100 different ways to formulate the problem, but all solution is equivalent of matrix inversion. So all the efforts of linear algebra has been to find a very good method to invert a matrix so that everybody across domains can use it. That's really where this idea of singular decomposition, etc., condition number, least square technique, so many things have come. Okay. So what can we do knowing that matrix inversion is a bad problem? Then we don't have to worry about maths. We can go to philosophy and ask Buddha to solve, and Buddha did solve this problem. We'll come to that. That's called the so-called Buddha's middle path. The middle path idea is the following: matrix inversion is adjoint of the cofactor of A by determinant of A. It's a very bad problem. The other way is inverse of A is itself. A good example for such A is identity. So if you have Ax equal to B and A is identity, it simply says x equal to x, no big deal. You can't do anything with it. But if Ax equal to B is given and you want to solve for x, find inverse of A, x is A inverse B, it's a very bad problem. So either it's a useless problem or a very bad problem. Can't we have anything in between these two extremes? One does nothing, and the other thing we don't know what it does, because cofactor tracking of coefficients, etc., beyond 3 cross 3 is a nightmare. So there is a middle path, like as Buddha said, Uh, so we should have a inverse which is not itself, but the inverse should not be as bad as this. So how do we go about that? Okay. To do that, we will see a contemporary problem of digital video. Okay. We all, even now, this is broadcast in the manner that I'm describing. So we have images which are shown in succession to get us an idea that it's continuous, which is called the persistence of vision. And then you want colors, you can do in 3 formats, RGB something. Let's not worry about audio because it's separate. So the problem with video processing is that it needs huge data compression. Okay. Typically, given 20 images, I must be able to reduce it to effectively the size of one. That is, compress each to 1/20th, sometimes even 1/50th. If you're looking at a video on the mobile phone screen, small screen, you need this orders of compression. Okay. But when you compress, you need quality to be maintained. Okay. And the compression ratio is related to image fidelity, meaning if you compress too much, you don't recognize what it is. But if you don't compress too much, you are not able to transmit or store. So I have a very hopeless situation where I want to compress a lot, at the same time retain the quality. So I must find out what can do this. Okay. And it's a huge data burden. Let's not worry about that. So we'll see how the problem solving approaches has emerged. Given a problem, solve if necessary, losing sleep. It's been historically, traditionally, and a very pedagogic approach where you bulldoze and slog it up to solve a problem. Okay. And many of the problem solving, classical problem solved has been like this. It includes the way Fourier, Gauss, and others work. Now, a slightly evolved approach is given a problem, do not solve directly or as given, instead try cousins and relations of the problem. These are also done political and historical. Of course, now copying an answer and plagiarizing is a very common thing. Okay, you have to be very careful today because academics in the large is more to do with plagiarism than with work. Okay. But a modern approach is try transforming the problem into an avatar which explicitly or easily yields the solution to the transformed problem and just simply inverse transform the result. So this is typically what is. Now comes what kind of transform to use. It will be good to use the transform in a matrix representation. Then question what kind of matrix. The matrix must be invertible, so choose it carefully. We have options, what type of A or what type of transformation. Very interesting if you look at dot product, which simply says the dot product of two vectors is 0 if the two vectors are orthogonal. Okay. So we did this in class 11 or 12, but a more mature version of this is this. What are the best choices? We saw the Mesopotamian civilizations breaking a triangle along similar sides. We got a transformation matrix representation 1, 1, 1 minus 1 or half, half, half minus half. But if you take a 2 cross 2 matrix, which is 1, 1, 1 minus 1 and invert it, very easy, just take the determinant, transpose that, multiply, divide by determinant, you are going to get the inverse. So the inverse of this case similar so happens that it is simply transpose divided by determinant. Transposing is easy because it's just flipping the rows and columns. So there are matrices which have the property that A into A transpose is identity. Okay, such matrices are orthonormal. So it is orthogonal. And if it's orthogonal, you can always make the length one. This is really what the Buddha's middle path really is. So Buddha's middle path in linear algebra simply says, don't go to any arbitrary matrix. Don't go to identity matrix. Choose a matrix whose rows and columns are orthonormal. And how many such matrices are there? There are infinite such matrices of any size you want, period. 90% of the engineering problems are solved, because this is what one good example is the cosine matrix. Why the cosine matrix is, it's a cosine discrete function. You have done this in class 11 and 12, where instead of summation, you took the classical integral. Find the value of definite integral 0 to 2 pi cos m theta d theta. Okay. And you finally calculate all that. You take product cosine into some form and break it up, and then substitute and find out. Then you get an interesting situation which simply says cos m theta d theta is 1 if m is equal to n. It is 0 if m is not equal to n, period. So it simply says cosines of different orders or different harmonics are orthogonal or orthonormal. So just use that function as rows of the matrix in a discrete form. That's all the trick is. So this is it. You see, two functions are orthogonal if the dot product is 0, and it so happens that this function cos 2i plus 1 p pi, 2i plus 1 q pi is 0 if p is not equal to q, and is equal to 1 if p is equal to q. So just use the function and you get a matrix like this. For those of you who are not in engineering, this matrix actually is a product of cos m theta, cos n theta for m equal to 0, n equal to 0, 1, 1. Horizontal cos m theta, m equal to 1, vertical cos n theta, n equal to 0. So from white it goes to black. This is 2. From white to black, back to white. White to black to white, so on up to 7 times. This is column wise. Same argument row wise. Finally, this is a function which is product of cos 7 theta horizontal, cos 7 theta vertical. So 49 changes total. Okay. So this is the matrix. I use this matrix as a transformation because I know the transpose of this divided by the determinant. If it's orthonormal, the determinant is 1, is simply the inverse. I use this and make this. So I standardize. Typically, for an image of a face, we break the image of a face into 8 by 8 matrices for some other reasons. Let's not worry about that. Then we take the discrete Fourier transform or the discrete cosine transform. In this case, you can still take the Fourier transform by making 8 cross 8 into another 8 cross 8 block by even symmetrizing, taking the DFT, because we know a result. The Fourier transform of a even function is cosine. Okay. So you make a even function and do DFT, is as good as getting the DCT. Okay. You do that and do some quantization. Don't worry about all that. Those are engineering techniques, and it looks like this. Okay. There's all justification. So I have an image in 3 formats because it's color. It could have been RGB, but today it is in YIQ, YUV, YCBC, or any 3 coordinate system. I take one portion and break it into 8 cross 8 block. I do the discrete cosine transform, which is an orthonormal transform for this. I get the transform coefficient. These transform coefficients are real. I want to convert it into binary, so I quantize it into 8-bit or 16-bit quantization. So these are the quantized discrete cosine transform values, and I do some, don't worry, I do some specific coding which allows me to compress a lot, which is called variable length code and etc. How I quantize is one table. How I did the coding of this is another table. I put all the coded value along with how it was coded with what tables into one file, and millions of such files are sent. These files are eventually done like this. So we will see this. You transform it. Okay. Then you do DCT, quantize, you compress it and send it. We will not worry about that because it's 8 cross 8 block. We will see how it looks. These are the quantization tables. Again for 8 cross 8, which means on a matrix, if you have the 1, 1 coordinate value, that coordinate value of the real number is divided by 16, whereas this 7 value starting from 0 or 8 if you start from 1 is divided by 99. For some obvious reasons, you'll see the lower triangular of this matrix has big numbers, the upper triangle has small. This is for illumination, this is for color. Color, only the top 1/4 quadrant has some variation, all others have very big numbers, don't worry. So this is a big matrix of a image or a face. I take one portion which is 8 cross 8. These are the real numbers for this. When I do the DCT, when I do the orthonormal transform, I get this. All these are relatively small. Therefore, when I divide these small numbers by big numbers, I get this. See, all are 0. Discard them. Only these values are important. When I want to see the image back, I reconstruct this. This was 32. The first position had to be it was divided by 16. So I now multiplied by 16. I get 512. So this was the reconstructed quantized DCT. I do the inverse DCT, which is transpose of this twice because it is row and column, and divide it by some number. I get this back. So the original matrix of 8 cross 8 had these numbers, 200, 202, 189, so on. And the new matrix I get is 199, 196, etc. Now, how good is this? It is approximately good. In fact, it is amazingly good because the error between the two is very small. Very small errors are undetected by eye and ear. Please remember, the success of all engineering products lies in the fact that very small errors are either not noticed or are not important, or the human can put up with that. So if you do this, you get this, okay? You put all those files into a frame, you say it is the start of an image, end of an image, all the frames are there. In each frame you have scans, headers and tables. And each of the scan has header and tables and particular segment, and each segment has blocks, 8 cross 8 blocks. If you pack all this into a huge thing, you get this. This is how a DVD is made. The success of DVD is because there is a orthonormal transform whose inverse is simply transpose of that. So the linear algebra problem of DVD is given x, find A or choose A, transform that, AX becomes B, you take that B and get back X by doing A transpose B equal to X. This is basically A inverse. This is the problem. So the encoder DVD is AX equal to B, that is given X, choose A, create B, and the decoder is given B, choose A in its inverse form, recover X. The whole of the world lives on such things today. Okay? What all? Plenty. Everything of these modern electronics and surveillance, radar problem, torpedo problem, missile problem, drone problem, your 5G communication, sonar, CT scanner, whatever artifacts you today use, most of them have this. And most of them actually use the idea of orthogonality. In fact, orthogonality, if you ask me, if differential equations dominated ideas 150, 200 years back, orthogonality has dominated at least the last 20 years. Okay? It will continue to dominate for some more time because the principle of orthogonality seems to be the best humans can do, in the sense humans want to do a lot by being lazy. That is, by doing very less, they want to gain a lot. And orthogonality helps. In fact, this was sensed by all the early mathematicians. That's why you have Butterworth, Chebyshev, Hermite, so many names associated with polynomials which were orthogonal. All those orthogonal polynomials were the way to solve differential equations in a much easier way than the standard form or standard approach. So orthogonality was sensed, but today orthogonality is the basic principle. Okay, historically orthogonality was identified as a way to get out of difficulty, but today orthogonality is the first principle before you start designing anything. Okay, more interesting when ax is not equal to b. That's an interesting problem which is more related to practicality, meaning even though you want to solve ax equal to b, very few problems actually give you consistent solution as ax equal to b. Almost all the interesting problems are either ax greater than b or ax less than b, which simply means ax will be equal to b plus or minus an error term. Okay, this really doesn't have a solution, so we try approximate solution and we solve for minimum error, more likely minimum square of the error. That's how this idea of least square error, minimum square error, method of least square. If you really want to solve it in modern language as ax equal to b, it simply says solve for x as a transpose a inverse a transpose b, which is a linear least square solution for this, which is also the generalized inverse, so on. But what is interesting is Gauss encountered this when solving a problem of celestial mechanics. Okay, one reason why all these interesting ideas emerged, people were doing very nice things, is because they were actually solving very interesting, useful, and realistic problems. They were looking at telescope, collecting data, referring to old tables starting from Galileo, Tycho Brahe, and so on and so forth, Johannes Kepler, and verifying realistic data and looking at problems which were not solved or which were observable but could not be interpreted, so on and so forth. Okay. So in this method of least squares, which Gauss did, please remember he solved the method of least squares as a geometry problem on a paper like this. Today we do it a little different. Okay, this is that famous least square estimation at the, who in 1798 at the age of 18 invented the method of least square. So there is a astronomer who discovered the Sirius had been able to track it, went behind the sun, it was not spotted, etc., etc. And then there were many attempts, and as usual, the German astronomer could relocate exactly where Gauss had predicted it. However, Gauss did not publish the method until 1809, when it appeared in the volume 2 of his work on celestial mechanics. Okay, so this is in Latin. I don't have skill to read Latin correctly. Okay, but what's interesting is the following. Today, what you say method of least squares, okay, fitting data, which is most common problem in statistics and data sciences and machine learning today. There was a big fight between Legendre, who published the method of least squares in 1805, whereas Gauss had actually started it in 1798, solved it in the middle, didn't publish it. He finally published it in 1809 in a very complete form, what we know today, and it's a full stop. What Legendre published was comma, not a full stop. Many more things were yet to be done on that, but Gauss did that and closed the chapter. But for a long time, there was a debate and fight between them. Legendre claiming credit for the least square, Gauss refuting, saying he had already done it much earlier and did not publish, etc., etc. I think history finally records that Gauss definitely did better, even though Legendre published it earlier. Okay. So what about this linear algebra today? All these things. If you look at your MPEG audio player, uses linear orthonormal transforms, all your ECG, CT scanner, your PET scanners and robot assisted surgery, all this medical field today is actually dominated by an idea which goes to Fourier. Okay. Uh, Interesting character. Okay. He was a mathematician, physicist, historian, and an administrator. Uh, Amazing thesis advisor, Lagrange, and amazing teachers, Laplace and Lagrange, contemporary of Bayard Savard. His favorite student was Dirichlet. He was made famous by D'Alembert because D'Alembert put his money and published his work on heat conduction uh, 2 years after his death. So Fourier never saw his work published because uh, Laplace and Lagrange, others, many of them were very critical of his Fourier series expansion idea, and he actually stopped a lot of mathematics which he could have done, but he actually did very good work as an administrator, and he started what is today known as Institute of Egypt, which is a historical archaeological study area all about Egypt, and the best place to study about Egyptian civilization is in Paris, not in Alexandria. Okay, so we all know about this Fourier series, but what's interesting is today the Fourier methods as a discrete Fourier transform dominates the entire imaging field in medical. Okay, so you have a profile and this equals this plus this harmonic decomposition. Similarly, if you look at a 2D function, it equals this waveform plus this, and all kinds of reconstruction algorithms, etc. So when you put matrix representation and Fourier method, if you put both of them together, you get something amazing, and that's the discrete Fourier transform matrix. So Fourier transform is very useful. You cannot do it. You could modify it as a discrete time Fourier transform and do some paperwork calculation for finite terms. But if you put it as a discrete Fourier transform, please remember, from Fourier transform to discrete Fourier transform, it's an approximation. From DTFT to DFT, it's a further approximation. Okay. So it's a sequence of approximations. Each approximation results in small errors. And the beauty is life is full of small errors. Okay. Some of you logged in 1 minute after the talk started, and some of you may have logged out before the talk ends. And my constant talking has not been of uniform modulation, so on and so forth. Okay. Reality and practicality also is like life in this, in the sense approximate least square solutions are not only feasible but occupy the world of practice. From lunar orbits to CT scan reconstruction, all of them have small errors which are tolerated. Okay. For example, the lunar mission by India, which failed 2 years back, it was correct, very small error, right from its launch on Earth all the way to 30 or 40 feet above the ground on Moon. But the last 30 feet, it had errors larger than tolerable limits, and it failed. Okay, so it's a sequence of small errors that really works. Okay. So this is how the Fourier transform thing works. I have a discrete signal sequence x of n. I take the discrete Fourier transform, I make it discrete frequency components x of k, I do the IDFT. But it's really not that. We had a continuous time function we could do Laplace or Fourier, we did this, and etc. etc. Both were infinite in both domains. I made it discrete and finite in both domains, all approximations. So it's an exponential representation of a finite duration. This is the discrete, forward discrete Fourier transform, and the inverse discrete Fourier transform, which is simply 1 by n, the complex conjugate of this. Okay. So if you really look at the matrix form, you get this. Okay. So this is x, ax equal to b. B is on this side now. So b equal to ax type. And x is a inverse b. And it so happens the inverse of this is simply complex conjugate transport divided by n. That's it. So very large n can be done. But what's very interesting is if suppose n was 2, this so happens that the Fourier transform is equivalent to a plus b and a minus b. Therefore, if I have a, b and I get a plus b, a minus b as a Fourier transform, I can put it in a matrix form. That matrix form will be 1, 1, 1 minus 1 times a, b will give me output a plus b, a minus b. So this simple hardware circuit is actually the discrete Fourier transform in hardware, 1, 1, 1 minus 1. And we saw that 1, 1, 1 minus 1 in the Babylonian civilization when they were cutting a odd dimension land into 2 portions. So if I now do that, this came about. The so-called algorithms, okay, fast Fourier transform, okay. The fast Fourier transform algorithm is interesting for many things. First, it's a further approximation to the DFT. It does calculate DFT very quickly. So it is an algorithm to calculate discrete Fourier transform, which is a unitary transform, okay? Hermitian, more than unitary, Hermitian, because it is complex. So it's complex conjugate as its inverse, okay? Gauss had some idea very similar to this, but did not get into the kind of structural formulation in a matrix form like we do today. Why this is interesting is because it's one of the greatest algorithm in the history of time. It emerged at a point where mainframe computers, apart from routine data processing, were projected to be useful if only an interesting algorithm could be programmed on that. And one of the earliest amazingly successful algorithm that was coded and proved to be useful happened to be this FFT algorithm by Cooley and Tuckey. They did both versions, the decimation in time and decimation frequency. What they did was they simply said, you can find algorithms which builds on the idea of unitary or Hermitian transforms. And the inverse is equally easy because the inverse of unitary or Hermitian transforms are simply transpose or complex conjugate transpose. Okay. Now, what really happened is because an algorithm could solve a problem on the computer, people were told learn about computers and learn about algorithms and a programming language to do. So for the first time, algorithm as a solution to a problem was accepted, popularized. We soon had the branch of computer science emerging out of this. So I think any computer science degree program cannot wish away the fact that the FFT algorithm has played a significant role in creating the discipline of computer science, what we see today, okay? So this is the idea of projection, which you do in coordinate geometry, okay? You have this, you can project it onto this, but you can also project it onto orthogonal components. And the dot product idea works, and Gram-Schmidt orthonormalization works. I can do the same in projection in the spatial domain, XYZ coordinates, or projection in the frequency domain in the Fourier space. So projecting it not in the coordinate system that we use or create the data, But in the Fourier space is the central part of all your modern medical imaging. This is how it works. So you take the brain, do virtual slices, and on a thin slice you do a two-dimensional DFT, do the projection in the Fourier domain, and it works. This is how you make all your scanning issues. We could have both discrete version of one or two-dimensional. You do the projection, you do some sample backpropagation algorithm, or you do this and you do the inverse Fourier transform, what is called multi-slice CT. That is, these are the bread slices, multiple slices. So the whole organ is created with multiple slices, and each slice is analyzed, packed separately, and it looks like this. Of course, one can do all kinds of scanning, radial, helical, whatever. So you do mostly the Fourier transform not in XYZ coordinate system, but you do the cousin. You do the Fourier transform in, let's say, polar coordinates or spherical coordinates, and idea is the same, only thing the coordinates change. So now the last slide I'm going to show and allow some discussion to happen after this is the question is why should people not study linear algebra? It is so useful, so amazing. I'm sure somebody giving a talk on functional analysis on topology can do the same. So I'm just saying from a utilitarian point of view, I don't think there is any subject as useful as linear algebra today. And I'm sure in future it will be a more useful subject will be statistics. But statistics in large data actually relies a lot on linear algebra because a large amount of data, the geometry of which is captured in linear algebra more efficiently. And what we actually do is some kind of geometric processing, okay? So what do you think of this topic? Does it motivate you? You don't have to give me, but you have to give yourself 5 reasons for not doing linear algebra. Now, if you want to do it, we can see what can be done now or what will you do. Of course, there are some interesting research ideas called ethno-mathematics, which traces back roots of what we see today. And there's an interesting BBC documentary clearly saying that Fibonacci and others who eventually led to Newton to do calculus, much of the critical idea of infinite series, sequences, ideas of limits had already come from Kerala School of Maths in Guruvayur. Okay, so you also need to look at the interdisciplinary outlook because you want to look at electronic products, but you also want to know the maths behind it or for it. So that's also very important. You can't do, I mean, barring a few people, you cannot do maths for math's sake. And the majority of the engineers cannot do engineering for engineering sake alone. You need a little better outlook to enjoy, appreciate, convey, build, refute, improvise, enjoy, so many things, okay? Well, I think I'll stop here, but when I give references, it is remembering 2 of the greatest gurus of linear algebra in the world today. Definitely one is Gilbert Strang, who has a book Linear Algebra and Applications. 5th edition has come, plus his 48 hours of video lecture on open source, open courseware MIT. But more for us, our Professor Vital Rao or Vital Rao. He has been the vital teacher for Indian Institute of Science for 40 years, I know that. His video lectures on linear algebra from NPTEL, but also parallelly every session in the NPTEL I think has been put on YouTube so that people who don't have access to NPTEL material can also access. So nice and thoughtful of him. Plus my own personal experience of sitting at least a dozen times a course on linear algebra by Professor Vittal Rao. That has been the high point of my academic journey, just enjoying his courses. Yeah. So I'll stop here. If there are any questions, comments, discussion items, we can take now. We have about 10 minutes time. Yeah.
Sir, I can take around 10-second pause and then we'll continue because in the live used YouTube.
Okay. Yeah.
Sir, I have few questions from
Yeah.
the participants. I'll just read that. How do we access these library? Is there any online access? Is one question.
To which libraries?
Maybe the one you have shown, the ancient evolving of all those. linear algebra.
Those things are all very well documented. They are available in any archaeological departments. Some there is a global heritage of such things available. Google Images will actually give you quite a lot. Most of it I have taken is from Google Images.
Okay, sir. Another question. In present scenario, with all hottest applications of linear algebra being in machine learning or artificial intelligence, computers do all the computations, even computing what algorithm fits what problem the best.
Yeah, so one of the problems we have today is that they think there is a black box like machine learning. You simply put your data or problem, whatever it is, whatever comes out has been designed so well, you will accept the answer without questioning, which is a very bad thing to do because they can also go wrong very badly, mislead you. That's why it's very important for youngsters to actually track a problem from source to finish, at least 3x3, 4x4 problems. I think one should get a firm grip of trying to solve a complete solution of 3x3, 4x4, even if it takes a little time. But unless you are sure how it is working, you will not know two things. One, if it goes wrong, you will not know what has happened. And if it has gone right, you will not know why it is right. So this kind of putting some program and making things work is useful. The industry will appreciate that. The industry will make a lot of money on such things because they don't need people to think and solve. But in your own interest, please don't do that. You learn to solve, enjoy, appreciate. Maybe you can, in some cases, do better than the machine. But at least when the machine does the job for you, you will have a gut feeling whether it's right or wrong. Don't miss that internal knowledge. And it's a very strong appeal for the younger generation, which gets a lot of reward every time they take shortcuts.
Thank you, sir. Sir, why are the blocks chosen to be 8x8?
The blocks are chosen to be 8x8 because there is, if you put 16x16, it's a power of 2 because we want to use DFT. DFT works very well when it's power of 2 because FFT works very efficiently for power of 2 size. We could have done 16 by 16, but then I would have had to store pretty close to 256 coefficients. Whereas 8x8 is 64, 1/4. So the complexity is less. And less than 8x8, the error is greater than 2%. I said it makes small errors. So if it is less than 8x8, the error is greater than 2%, and error threshold of a normal eye, not Raja Ravi Verma's eye or Leonardo's type of eye, a normal eye, the threshold appears to be around 1.5 to 2%, which means if you do error more than that, I will notice the error. So basically you want to fool the eye, telling that no error has happened. So you must do less than 2% error. And the threshold for 2% error is around 8 cross 8. I could have done less error by doing 16 cross 16, but that would have created more computational burden. I could have done more computational efficiency by doing 4 cross 4, but I would have crossed the 2% error. So this is how engineering works. Engineering, psychology, physiology, all if you put together, you will get some of these numbers. That's why I keep telling engineering alone will not work. Mathematics alone will not work. Engineering, mathematics, psychology, philosophy, all these subjects contribute to a very interesting success. In fact, the 8 cross 8 is simply physiology, psychology, mathematics, and computer put together gives you 8 cross 8.
Thank you, sir. And the last question, sir. Do we relate linear algebra with fuzzy logic?
See, don't get mixed up with this. If fuzzy logic gives you numbers, which I know it does, these numbers, if you put it in a matrix, becomes a so the idea of fuzzy linear algebra, all that don't get linear algebra. You're doing. You're basically today talking of matrices by and large. There are other linear algebra functions and all. Let us not get into that right now. 99% Janta will do linear algebra as a matrix. What is a matrix? Matrix is just an array of numbers, real or complex. Where do you get these numbers? If you get it from a fuzzy system, excellent. You can still do linear algebra. Linear algebra is all about solving Ax equal to B. How did you get the numbers? You got a Boolean logic, you got a quantized value, you got a fuzzy logic, you got some approximation, interpolation, whatever you do. That's your choice. Don't mix up the source of numbers, the techniques of getting numbers with the methods of solving the numbers.
Thank you, sir. Thank you for such a wonderful talk on pedagogy and linear algebra. You started with how linear algebra evolved since 500 current era till dates, the modern applications, including the DSP, digital image processing, Fourier transforms, etc. You touched upon all those linear square techniques, orthonormalization, Gram-Schmidt process, SVD, everything. Thanks a lot for such a good talk, and thank you very much, sir.
Thank you very much, Professor Govindraju. Thank you very much, Ramaya College Maths Department, Professor Ramesh, everybody. I only wish this talk was not online, but offline. Maybe someday we will catch up on that. Thank you very much.
Sir. We all wish that, sir. And again, in spite of your very, very busy schedule, you accepted our invitation and made it a success. Thanks a lot, sir.
Thank you very much. Thank you.